and thank you all for joining here in person, as well as folks online, for our EREC seminar series. Today we have Dr. Nikolaos Tziolas joining us. Dr. Tziolas is an assistant professor in the Soil, Water, and Ecosystem Sciences Department, and he's located at the Southwest Florida Research and Education Center. Dr. Tziolas' research program deals with developing AI techniques to support informed decision-making in agriculture and investigating multidimensional and integrated sensing approaches using AI techniques. So with that, Dr. Nikos, I hand it to you.
Yes. It's my friend. It's not working, eh? So good morning. Good morning. First of all, thank you, EREC, for hosting the event, and especially Django for inviting me to give this presentation. As Django said, I'm Nikolaos Tziolas. I'm an assistant professor at the Department of Soil, Water, and Ecosystem Sciences. And today I'm going to give a short talk about how conversational AI can support simplify decisions in agriculture in order to access information about soil and crop insights. So, in brief, I'm going to have a very short introduction about the Soil and Artificial Intelligence Laboratory. Currently, we are based at in Immokalee, at the Southwest Florida Research and Education Center. Then I will move with some definitions, with some techniques about digital soil mapping, and then we are going to present tools that can be used in order to simplify the access in the information. So SoilBot, the GaiaBot. Finally, I will present some next steps and some ideas that we have in our mind in order to optimize the tools and the models. And at the end, I will present you my team. Sorry. So I started almost 2 years ago. I'm pretty new here. We started just with some goals, and now we have a fully operational laboratory at SWFREC. We have already 6 people with some PhD students, some OPS, and some postdocs, and we are always recruiting. I will go later on this one. So, what is the lab research focus? What we are doing in with AI, and how we apply AI in soil science. So, our laboratory focuses on leveraging artificial intelligence techniques. And as you can see, the diverse data streams from satellites, from in-situ sensors, in order to enhance, first of all, the predictive performance of the products, of the maps, of the soil maps, of the crop maps, and also to strive to democratize these scientific outputs to a broader community, to people that they don't have expertise in order to access these digital products. So in order to do this, we work with a lot of sensors. We work with sensing devices that can capture the spectral information that are not visible by the human eye, but can be later on decoded in order to give us some insights and translate these raw numbers into crop and soil maps. Then we use a lot of satellite products in order to cover bigger areas. Usually we work a lot at a global level. So we work a lot with satellite in sensing devices. And using this kind of data, we start applying our passion. We start applying artificial intelligence techniques. We develop our own techniques, our own algorithms, in order to uncover these insights that are invisible to the human eye, but can be very, very useful at the end of the day. So we are trying, again, to translate numbers into maps that can support agricultural productivity and environmental monitoring. And sometimes, because technology is expensive, technology doesn't fit in all the solutions, we develop our smart integrated systems. We utilize 3D printing technique, photonics, in order to develop our own sensors. So this is the data. And what about artificial intelligence? Now artificial intelligence is a trend. Many of you, maybe you have already heard about machine learning, deep learning techniques, large language models, but just to make it simple, artificial intelligence is just a field in the computer science that enables the machines to simulate in a way the human intelligence. So we would like to just do things that a human can do in a simple way by a machine. As I said, different machine and deep learning techniques have already presented. You can see examples, many examples about classification of crop, soil estimation properties, maybe some prediction of pathogens or some disease prediction in the crops. So I'm pretty sure that you're familiar with these techniques. Also, you have initiated these activities the last 5 years. But a new trend that I'm pretty sure that you have here, like ChatGPT, is generative AI. Is this domain, is this field of AI that can create new content, such as text or images, by learning from existing data. So there is a kind of interaction. We just have an interaction. We chat with ChatGPT or these generative AI tools, and we generated responses, images, and whatever. And later on, we will see how we can use this into agriculture domain and how we can support agronomic activities. So a small part that we would like to see also later on is these large language models. I'm not going to dive into details, but just to let you know that large language model is a specific domain that is between the edge of generative AI and deep learning techniques. And this is, let's say the hidden power behind machines like ChatGPT. So back to the soil, back to our interest, the reality. There are multiple products that can used in order to provide information about soil maps. Digital soil mapping is a field that has activities more than 30 years, but there are limitations. First of all, as you can see, the current products, or many of these, they have a coarse resolution. A resolution is the pixel size, and when I mean coarse is the limitation that cannot give us an opportunity to get insights within the same field. So as you can see, if we use the left part of the map, we cannot see difference in our field in order to decide how we can make different practices. So one thing is the coarse resolution, and this can be overcome by the integration of new data, big data, and advanced technologies. But in order to do this, we have to develop the tools in order to reduce the latency. Sometimes we talk about precision agriculture, and there is a procedure that we are going to the field, we capture an image with a drone, we go to the lab, we analyze the data, and we provide to our stakeholders, to the growers, a map after 10 days. And now we have a completely different growing stage. So reduce the latency is one challenge. And for sure, the last challenge is about accessibility and usability of these products. As I said, there are some non-experts that they don't have the background in order to get access of this information. And we will see later on how we can overcome. So in order to reduce the latency, the first year in the University of Florida, together with some colleagues from Europe, Ellie and Nikos, we develop a cyber infrastructure. We develop a cloud system able to download in an automated way satellite data that can cover the entire state of Florida without spending time. So we just upload the system every day in an automatic way. We download the data and we collect this data in our repository. So we have for the last 4 years, covering the entire Florida, we have terabytes of this information in a format that is, as we said, analysis-ready data. We can use this data directly in order to apply later on our algorithms in a simple way, and we can update our products. So if you request for us a map about the crop health of your field, we can deliver it in seconds, and we will see later on how we can use it. If we request for us the soil map, we utilize this analysis-ready data from satellites, and we generate a product with artificial intelligence algorithms. And how we do this? We utilize the temporal resolution. We have now an opportunity to monitor our Earth, our fields, our oceans, everything, every 5 days. Some satellites provide also a daily coverage. So we analyze all this time series of data, and we keep only the information that we really need. So what is about us? It's the bare soil pixels. It's the pixels that represents the true soil. And what I mean by true soil is what we can capture with satellites as a fingerprint of the soil. I usually use this example in order to make it very, very simple. So you can imagine a fingerprint with unique characteristics that represent Janko. Another fingerprint represent me. So if we would like to classify or estimate or predict, we use this fingerprint of the target in order to make correlation with artificial intelligence and estimate properties. For sure, we have other limitations like the roughness or the partial cover vegetation of the fields, but we have developed data mining techniques and thresholding approaches in order to remove the noise and make a better predictive performance for our models. All this is a combination of multiple studies. We work at a global scale, and I'm not going to dive into details about AI, but for sure we can discuss later if you want. But the ultimate goal is to generate maps. And we would like to generate maps, as I said, for the entire Florida. Usually we did it for the entire world. So based on these artificial intelligence techniques, we managed to improve the accuracy of the estimation of 5 soil properties. For now, we have clay content, cation exchange, electrical conductivity, pH, and soil organic carbon. We also work with soil organic carbon stock. The system is able to generate this map on request or at an annual level. And the system is modular. And what I mean by modular, later on, maybe we can include other properties and it's feasible. So we have to retrain the models and we have to make a new map, maybe for nitrogen. And what else I mean by modular, the system can be applied to a specific area. So if someone has data in his area, we can train the model and we can provide the maps more detailed for a specific area. So if a grower or if FIREC has a lot of data and they would like to make more detailed maps, we can specify an area, a region of interest, and we can retrain the model and generate the maps. For now, we provide the maps at 30 by 30 meters at the global scale. This is just an example of Florida, but we are going to release the version 2, and there is 10 by 10 meters. And I think it's good enough in order to see this variability within the field. And as I said, we have also the opportunity to perform this at the annual or semi-annual level. So just to demonstrate, we have the students, my student Anastasia and Yanis, they have developed a simple graphical user interface in order to give an opportunity to the user navigate and get some information about soil properties, as we discussed before. So you can navigate in the area and you can click very, very simple the soil property that are you interested. And then you can make a search by coordinates or making a polygon in order to go to a specific area and get some more detailed information. So for sure, a grower or an extension agent or even a researcher can access this information and can decide how I can manage my fields and how I can work further with this product. So looking forward, we said that now we have a new reality. The reality is to use our smartphones in order to access information. All of us, we are daily users with the smartphones. So instead of having this interactive platform and navigate, we think that, okay, let's try to think something different. Let's try to develop a simple application in as a chatbot in order to give the possibility to someone with non-expertise to access this information. And we said that we have Telegram, that we have WhatsApp. So both of these communication apps, they have multiple users. Telegram has more than 700 million monthly active users. So we said, okay, we are going to make a chatbot specific to Telegram in order to give an opportunity to the user to access this information. So you can go to Telegram, you can search about SoilBot, and you can share your location. and simplify with a simple way, just pressing clay if you would like to access clay information, and you can get this information. Similarly, you can access also the other properties, the cation exchange capacity, the electrical conductivity, as we saw before. We are thinking instead of the map, just provide the real value. Maybe the map it's not necessary if you are in the field, but you would like to see the exact or a proxy estimation of the soil properties in your position. But also you can share your location. You can write that I'm living in Naples. I would like to know what is the soil organic carbon in Naples. Obviously, the example is not the best one because I select the city of Naples because I'm living there. But I would like just to demonstrate that we have the opportunity to provide the information from all over the state. So in Naples, here in the real position, also in Gainesville. So it's very, very simple to access this information. But yeah. So then we start thinking a little bit different, and we said that look, we are living in the era of GPTs, the generative pre-trained transformers. Maybe this is completely awkward as a term for you, but if you are thinking more carefully, it's what is hidden behind ChatGPT. And I'm pretty sure that ChatGPT is familiar to all of you. You are using in daily routines in order to polish your manuscript, to polish your emails, or even to make some analytics. So my students, again, Anastasia and Yanis, lead this effort and navigate among the landscape, among the environment, let's say, of the different GPTs, of the different generative pre-trained transformers. And we realized that we don't have a specific GPT that can combine the spatial information that we use in agriculture with these text dialogue component that is provided with the large language models. So we thought that, okay, maybe it's time to develop a tool that can combine maps and also large language text. So the students come with an idea and they develop the geospatial artificial intelligence analytics bot, Gaia bot. Gaia, it's coming also from the Greek word that is mean earth. So I think it's really, really relevant with what we are doing. So what is the vision of the team for Gaia bot? We would like to have a tool able to bridge the gap between satellite data and practical application using AI-driven workflow in a simple way. We have multiple satellites. I think that we have more than 10,000 satellites in orbit, but we use it very, very few of them. Mainly, we use just satellites in order to access information about weather, but we have many of these. So we would like to simplify the approach in order to be able to get this information in an easy way. So um, very, very quick, the Gaiabot has as a vision to provide to the users with real-time data. As we said before, if I need the crop information for my field, I need it now. And I would like to say, give the crop information for my field in order to support sustainable agriculture and effective environmental management. Again, we simplify here that we have lack of awareness, many satellites, but we need user-friendly tools in order to be able to access the information in an easy way. And this will enable us to have broad accessibility to people that they don't have expertise. I really like to see my mom using this kind of information even before going to the beach in order to ask what is the UV radiation. There are also products like this in the field. And if you can get this information, it's really, really useful in order to take a different decision, not in the domain of agriculture. But going back to agriculture and what is interesting for us, a simplified architecture about how these systems are works is that we have a user and we have the system. So the user, maybe a grower or extension agent, it is going to ask in a simple natural language, how are the levels of carbon sequestration in my field? And by the field, we have to define an area of interest. So we just draw a polygon. We indicate where we are now. And then we have the general framework when we have three different components: the natural language understanding, the large language models that we discussed before, that translate this information provided by the user, both the text and the coordinates, the region of interest, in something useful for the system that will enable us to move to the second component, to the natural dialogue management, and say, look, I'm looking for soil organic carbon in this area, so please go to our database, retrieve or generate this product, and come back again. And now we have the third component, the language generation. So having this information, the system generates this response, saying that the soil organic carbon sequestrations ranges from 50 to 70 tons per hectare, and this is your map. So this is what we generate with the system. So, to an example about the system, the user, here is the student, just define a polygon and start chatting with the system and say here, hey, hi, first of all, that's my field. And now we have a response from the system that, okay, it's great to connect with you about your field. What you would like to know specific about your field today? And the student, the user, start asking some more information, start asking information about soil properties. And this can be done in real language. It's not necessary to click. It's not necessary to have a specific knowledge about GIS. The student or the user just asks, what about the soil texture in my field? And the system just returns for all of these the map, the spatial representation of the products, but also some statistics that in your field, we have a range of, let's say, of organic carbon from 11 grams to 100 grams per kilo, with an average approximately of 36 grams per kilo. And it generates also a response that your organic carbon is within a reasonable range, but it can be very specific of the crop needs and whatever, et cetera, et cetera, et cetera. So then the user start asking more specific but also abstract questions. So how I can check the soil health indicator for my field. I have a background in soil science, but if you're asking me how I can calculate the soil health index, I have no idea. And there are several research groups in the academic community that they are still trying to find a formula in order to give a score to as a soil health indicator. So the system, considering also the crop type, is going to say to apply specific formulas that is not even known by the user, and make the calculations in order to return back a score. So the soil health indicator for this specific field is around 85%. And then the user is going to ask more and more information. Can I grow apple trees? And for sure, the system understands that, look, are you based on Florida? The climate type, it's not the proper one in order to cultivate, because apple trees would like cooler climates, but you can explore other things. But we will see later on other examples. So very, very quick how it works. The left panel is the interaction that we have with the system, the questions and the questions for the users and the responses from the system. And along with the questions, we have also the provision of spatial information. So we are giving the coordinates to the system. The central column is the hidden power behind the Gaia-bot. So first of all, we have a classification of the different intents. So when we said, hello, this is my field, this is recognized as a welcome inquiry by the system. But when we are going to more specific agronomic requests, we can see that it started to specify it as soil property or crop suitability or soil health inquiries. So we have an intent classification at the beginning. And then, based on this, we have the extraction of entities. So based on the soil property inquiry, we can see that the user requests something about the carbon sequestration. So we just extract the specific entity, the specific, let's say, keyword that will enable us to run a new model and access the information in order to generate the product. And then, as I said before, we have the generation of the language. We give a response based on the existing knowledge of the literature, of EDIS publications. We can see later on another example, and returns back also the relevant maps. So this is the way that it works. In another example, the user now is going to ask some information about a specific field by clicking, by drawing a new polygon, and again provide a welcome message and say that this is my field. And now we think that maybe we can provide some more information to the user about how he or she can ask more specific information. So the system said, should I irrigate my sugarcane tomorrow? But the user, let's go to the example, ask about the soil health. And as I told you before, just about asking what is the crop health look like, we got some products from the first system for the data cube that we discussed. So we can have access in seconds without specific knowledge in order to access how it looks like the field. And then the user asks again about some soil health indicators, etc., etc. But we have also another question that my field looks like a bit dry lately. Should I water my crops? And we think that irrigation is a critical component. So just by asking if I have to irrigate my field, the system said that you can water your sugarcane crops, and we recommend to apply around 30 millimeters of irrigation. And we recommend this because we estimate the phenological stage, but also we can see that there is no chance of rain tomorrow in the next days. So based on this, you can understand that we start access also information about meteorological data. So again, this is the interaction with the system, the user and the system. We saw that we provide some spatial information, some questions, and we have the classification of intents and the entities extraction. But in this case, the irrigation activate a new entity. So sugarcane planting date and irrigation, I have to access information about the meteorological data in order to calculate the evapotranspiration. And based on this, we estimate this data, we retrieve this data for the last 7 days. And based on a combination of the NTVI, the last meteorological data of 7 days, we estimate the evapotranspiration and give the possibility to the user to define the irrigation plan. So in the next example, and the last one for today, we go back to lovely Immokalee and say, okay, let's have another field. Let's draw the field. Let's try to design. Let's try to work with peppers now. Again, hello, this is my field. And we have this kind of interaction with the system. And the system coming back and say, okay, welcome to your field. Your field seems to be located in the southwest region of Florida. This is more than obvious because we are in Immokalee, and it's around 500 acres. So the user now is providing some key information and say that I'm growing peppers using fertigation, and I would like to see excuse me, some fertilization recommendations. So now we try to, in a simple way, to ask about fertilization recommendation and if possible to generate the fertilization maps. And as you can see, the system returns back that a response that you can apply 408 fertilizer at a rate of 30 libras per acre over a 30-day period. And the fertilizer formulations provide a balanced approach, etc., etc., etc. We provide also a potential application date that is March 29 of this year. We ran the example yesterday, and we have again a probability of precipitations around 10%. So we would like to apply fertilizations in days with a low precipitation chance. And going back to the hidden power, how we define the type and the dosage of the fertilizers. Again, in the left part is the interaction, but here we decide that a lot of good colleagues provide extension publications at the University of Florida. A lot of good colleagues also provide research publications. So we said that we have done already a lot of work that we can access in order to get some recommendations based on our needs. And we accessed the EDIS publications, we have an API, we have a system to connect the Gaiabot with the EDIS publications in order to see what Django is doing in sugarcane and get some recommendations about his experiments. For sure, there are many of these, so we restricted our interest in publications relevant to agriculture. We access around 7,000 publications for different crops, for different regions of interest in Florida. And we develop our model using the satellite data from NDVI or other vegetation indices, the soil type, meteorological data, but now also text. So we start integrating in our models text, books, research papers, not only spatial data. Very quick, we use let's say retrieval augmented generation. It's a RAG in order to enable us do all these things in the background. We decide to work with let's say the highest ranking, the 5 more relevant papers. Maybe we can extend this to 10 or 15, but for now we just work with information that we can derive for the first top 5 most similar EDIS publications. And we can extract from the equation of the user some key information. So fertilization rate, application methods, and chemical compounds. So this was the keywords that we use in order to train our model. And very quick, how we train this kind of model, the large language models, we use some kind of embeddings. I'm not going to go into detail, but as I said, you can imagine that embeddings turn words into numbers. So the word the soil can be displayed like 0.3 minus 0.14, and we use this number in order to calculate a similarity. And based on this similarity score, we have access to the most relevant papers in order to give a precise information to the user. I think I have some time. So as I said, we integrate the meteorological API and forecast precipitation for the next days, and we recommend fertilization on days with low rain probability. As you saw, the example of Immokalee, it was around 10%, so it's not bad enough, and we recommend to apply fertilization tomorrow. In order to generate the spatial map, the variable fertilization rate product, we don't recommend reduce input agriculture. We just say that, look, we can see that we have different areas in the field and you have applied more here because we can recognize a risk zone, or you have applied less in the other parts. So high vegetation in these areas, we use a combination of NDVI and other indices, are get penalized up to 20% reduction. So if we have a lot of green areas, it's not necessary to throw more. So we use just a threshold as a penalty. And low NDVI, low vegetated index areas are prioritized as the areas that we have to fully recommended rate according to what is proposed from this publication. So for the next steps, we got some feedback for our end users, from growers, for extension agents, and they really would like to see soil moisture products. So we would like to we already work on this direction. There are a lot of good colleagues at the University of Florida working in soil moisture maps, and we explore synergies with some of them. So instead of all the others, we would like to have also the soil moisture information in the model. Another example that we are already working is the augmentation of data resolution. Some feedback that we got is that, okay, 10 meters are good enough, but if we would like to monitor vegetation, we need more detailed information. So we retrieve information for satellites, and we apply some artificial intelligence techniques in order to enhance the resolution to 1 meter. And it works good, but since we would like to have this information for the entire state, we would like to validate it in more areas. For now, we have validated with good results. Good results, I mean the representation of spectral characteristics. So we have done it for ONA and Immokalee. It's the opposite, ONA and Immokalee. And we can derive detailed information. And yes, the last part, again, feedback from our extension agent and the growers, that we would like to have a direct collaboration with the growers. Now we are working in a tomato commodity in order to explore new applications. I know that irrigation and fertilizations are very, very important for farmers, but we would like to integrate also information about cost calculation. So if I would like to fertilize this area, what is the cost? And if I would like to reduce the input by 10%, what will be the cost? And since we have also access to the web browser, we can access also information about the prices of the fertilizers, and we can make in a really in real time a cost calculation about an irrigation plan or about a fertilization plan. I'm sorry. Special thanks, as I said to the beginning, to my team. Everything that you saw are derived by my students. They are working on this direction. They develop models. They cultivate their passion in order to do these things. Currently, I have 6 people, but we are recruiting. We need more people. So if someone is interested, let us know. We have new projects that are relevant also to the Gaia system. We work with some colleagues from Gainesville in a project from USDA and NRCS in order to further advance with more in situ data the soil maps for Florida State. So in the next years, we are going to provide more and more detailed information about the soil properties at the Florida State. And we have another project from USDA and NIFA that is funded, and it gives us a possibility to work with data from drones and ground robots. For us, as I said at the beginning, the data are the same. We just want the data in order to integrate the system. We have already automatized the procedure to analyze the data. And with Gaiabot to give this simplify access to user with non-expert background to work in a simple way to access this information. And that's all from my side. And since the topic is about conversational AI platform, I left more time for conversation with you. We really need the feedback. We really need the questions about the technical things. I can answer everything, but also suggestions. I'm really interested to understand what is problems in sugarcane, in tomatoes, in peppers, and what are the really needs in order to work on this direction. Yes. So let's take a few questions from the audience here, and then we can have folks from Zoom.
Nikos, thank you for a wonderful presentation. And I know you're focused on Immokalee and other places of Florida. So coming back to this area where we have a lot of organic soils, we have a lot of challenges in terms of soils, and one of them is soil oxidation and subsidence. And a lot of farmers ask, is there an easy way to measure my soil depth? Like, what is my horizon? You know, that's one of the things I look for. So I think that's something in terms of application, and I know a lot of people are working on that, you know, different entities. It's not an easy thing to measure. And the second feedback I would give, you know, you talked about the economic cost calculations. That would be awesome, because fertilizer rates are going up in terms of prices. Farmers need to make decisions in real life in terms, does it make sense to apply these fertilizers, or should I scale back?
Considering the second part of the question, as I said, this is also the feedback that we got for the extension agent and the users. For us, maybe it's fascinating to generate maps, generating maps with colors, working with algorithms. But at the end of the day, we have to translate this to environmental cost, but also real cost. And now we are working on this direction to have with some techniques real-time access to data in order to have the most updated prices. A lot of these pre-trained models have trained with data from 2 years ago. But yeah, the market of the fertilizers is crazy, and we have changes every day. And we are working on this direction in order to have real-time access and make the correct calculations. And I think this gives us also a possibility to develop what-if scenarios. So if I have to to give 100 pounds of fertilizer, what will be happened with 9 and what will be the cost. So for us, this is a super priority, as I said, and I fully agree with you. So in the first part of the question, this is more interesting for me because it has also some research questions. It's difficult to see with satellites and all this kind of data what you cannot see directly with your eye. We said about the spectral information and what we can see beyond the human eye, but looking at depth, it's difficult. What AI can give to this is to optimize the simulations. There are multiple researchers, it's not my field of expertise, but there are multiple researchers working with physical process models that just translate physical equations in a way that we can get some access to information that is really interesting for us. But these informations are these models, I'm sorry, is data demanding, and sometimes it's really difficult to run. So this is the way that artificial intelligence can support optimize the simulation time of these models. We have run a similar example about soil and water assessment tool in Europe, but we have never worked in depth. But for us, it's a challenge. If you have data and if you have the research question that can drive our passion, we are more than happy to collaborate with this.
Yeah. Thank you, Dr. Nikos, for the presentation. With relation to the parameters you are mapping, like soil organic carbon, soil nitrogen, CEC, these all parameters are very dynamic in nature.
Yeah.
And I see you are using the satellite images and you are updating them. But are these good predictors for these parameters, or do you need to use some other predictors which can be collected real time as well and create the model? Because I was creating some model related to soil organic carbon, and I found out like the real time parameter, soil moisture and electrical conductivity, CEC, are more related to soil organic carbon than the cover images, satellite images, and others.
What we are going to explore in the first USDA and RCS that I said, this dynamic role of the properties. So what we did now is to generate the independent variables. Since you have a background, let's say that we generate the satellite data at annual or semi-annual level in order to differentiate the input. And based on this, we can predict indifference. So we try to have this temporal resolution in a way to translate the dynamic properties. Back to your suggestion, I fully agree. If we can integrate a network, even with the meteorological parameters, or even with some stations that can provide electrical conductivity or pH constantly in a way that can be integrated in a system and make this automated, it will be really good. We ran this example in Europe. Unfortunately, when I came here, we didn't find this information in order to integrate in situ networks, but it's super important in order to address these limitations. Yeah.
Morning. Thank you for the presentation. Maybe. One question I had when you guys are doing all the satellite data, do you guys have any issues with the clouds? Because what we've kind of seen in our analysis of it over time, like, because we're a year-long crop, basically, we're trying to see things change over time. With the amount of property we farm, we run into a large portion of our property has clouds on it at some point when that satellite's going over. So when we're doing contiguous monitoring of that field over the life cycle report between cuts, we have a lot of issue with that. So have you guys done any research around how to handle that and how to kind of interpolate that data or backfill that data or whatever? Because I did see where you guys are on the previous slide where you're looking at the AI enhanced, the cloud was gone. So I was just curious if you guys are doing anything with that.
This one, right?
Yes.
Let's clarify for this. This is a product from Sentinel. It's 10 meters. It's provided open and it's completely free. This is what I said, the product that we generate at 1 meter with AI.
Yep.
And this is in the middle column is a commercial product from Planet.
Okay.
Planet is a constellation of CubeSats, small satellites that provide information at the resolution of 1 day.
Okay.
And what happened here, we just don't have the same time that we capture the
Okay.
images. So we don't remove the clouds. When we do the analysis, we consider and we have already the mechanisms in order to remove it from our analysis and be sure that we are not providing erroneous data. Because if we are going to translate this into a vegetation index and give an opportunity to you to get some information about your crop, this will be displayed as an area with low NDVI, let's say, with low vegetated areas, and you are going to fertilize this, and this is wrong. And when I came here, I had finished a project in Lithuania, and in Lithuania, we faced this project with problem with the cloud coverage a lot. So Lithuania has around 30 days per year with sunny days. And we integrate Sentinel, multispectral and radar data in order to avoid this issue. When I came here, I believe that I came in a paradise, no clouds, fully sunny days, but I realized that just we have sunny days because the clouds moving very, very fast. So for now, since we have this opportunity of 1 day or for 5 days this, we don't focus on the removal of clouds. We just throw out, but maybe you are going to have let's say, a gap in your image, but we are not working directly in order to give the decisions with the image. We are working also with the time series. So we know what happened before, and we have a kind of simulation of this growth pattern in order to get a decision. So for instance, in the fertilization, it's really, really useful in order to estimate also the crop phenological stage. But we are working on this. But I think 1 day resolution is good enough. If you are not have this day, you can go to the previous one. So when we ask in the system, can you say me what is the soil health crop index? We have some thresholds that if we have cloud coverage in an image more than 20%, don't get information from this and go to the previous one.
Yep. Yeah, that's kind of what we've seen because farming so much land, it's so expensive to buy imagery.
Yeah,
It's
yeah.
every day. So like if you're looking at it over time, the probability that you're going to be missing something somewhere is almost 100% each pass of like Sentinel-2. So I was just curious if you guys had anything to handle that because it's a problem for us
Yeah.
at least.
And this is the way that we work on this, the data accommodation in order to generate the image in 1 meter. I also believe that it's not worth for a farmer now to pay for a satellite imagery data. The current resolution is good enough. I'm not a big fan of UAVs. I have worked in Wageningen a lot with UAVs. When I decided to do my thesis, I negotiated with my professor that I will do whatever you want, but not UAVs. So yeah, I don't think that it's so detailed information. It's not necessary now. Maybe later on, but we have to understand what we can do with these products, and later on, if it's worth it, we can pay. It's my personal opinion.
Yes, for sure. And I think there's not a lot of product between what we get from satellite today and a UAV because it's like you got 10 meter, you got 2 cents.
Yeah.
There's not a lot in between that unless you want to pay a lot of money to get on a regular basis. My other question is, do you guys have the architecture for what you guys built out of the Gaia bot? Like what products do you use? Like which LLMs and all that kind of stuff anywhere? Or have you not shared that yet?
We have this under publication. We will try to get it also a patent for this. We are going to present it. I can provide you an architecture if you want what we are
Yeah, I'd be
using
curious
about.
too.
There are multiple models. We work with Llama, with some. We try to integrate also OpenAI and see what is the difference if we use our own model and if we use OpenAI. And we are still exploring, but for now we are using Llama. And as I told you, it's a combination. It's the combination of, come on, this one, the soil data cube that we retrieve the data, the meteorological and all these things. But if you are interested, for sure, I can provide you a rough overview of the architecture.
Awesome. Thank
Yeah.
you.
I thought it wasn't that.
Any questions on Zoom?
Yeah. I can hear you. No. I can see the participants. Maybe no question. Yeah. I cannot see someone. Or suggestions. If you don't have questions, I will be happy to hear about suggestions. What will be a product that is interested for a grower or even for a researcher? But let's talk about the growers. Samira talk about this cost calculation. So, oh, that's great. That's great.
No, going back to ground truthing and making sure these models are giving us something that is not, what is somebody told me, hallucinations. What do you guys do? I know for the nutrient recommendations, you get a lot of recommendations from fertilizers, but in terms of all this satellite imagery and telling you, and I understand the NDVI, but mostly on soil properties, do you guys do any kind of ground truthing to say, okay, this is the CEC that we're seeing with the satellite imagery and the predictions are the same as what we have? I'm just curious.
Yeah, for sure, for sure. All the models that we develop, the spatial products should be validated. Otherwise, it doesn't make sense. How the AI works, we calibrate a model, we learn to a young child how to talk, and then we would like to see if he or she can talk. So it's the same way that we follow in modeling. And as you can see, we have some ground truth data from from the USA. But as I told you, the product that you saw before, okay, here, I think it's this one, yeah. It's a product of a global data set. So we work with colleagues from all over the world. We have around 3.5 million ground truth data in order to develop our model. We explore different techniques. So a lot of them, they have good accuracy in some places because some places provide more data. And a lot of them, they have low accuracy, for instance, maybe in Immokalee because we don't have any of data. And this is what I told you before. Okay, this is a global product, but if you would like to make a specific product with the data that you have in EREC, you can do it. We can rerun the applications. You can fed your data. We have also developed some techniques in order to avoid data sharing. I really know that it's really difficult to share your data. So we try to use federated learning techniques in order to avoid this. And if we use data from here, the product will be very, very, very specific with a better predictive performance. Yeah. I'm trying to remember how many points we have from data compared to the 4 million that I mentioned, but I don't have these statistics now. But there are, for Florida, there are not a few. Yeah. Yes.
Are there any acreage restrictions? So like for smaller scale operations, or is this mainly looking at large scale operations for now?
About what? About
Like-
everything?
Like the acreage for the analytics, like if someone only had like a 5-acre plot kind of.
No. You can do it. You can do it. 10 meters can provide also some good information about the small fields. But maybe later on, the example that I showed you about 1 meter will be more representative. What else we are working also in order to automate the delineation of the field. So if we are see the opposite side, if you are going to design a very big area, probably you are going to include roads, you are going to include buildings, and we would like to find a way, we know it, but we have to integrate it in order to focus only on the field. So if you would like to design a polygon for the entire area, and if you are getting some roads, maybe you are going to get some erroneous results. And if you are getting a pond, maybe you have some erroneous results. So this is the reason that we focus on examples that we would like to have specific fields. Otherwise, the user can upload a shape file, the borders of the field, and can get the information about his region of interest. But there is no restriction for the minimum size.
One last question.
Last question.
So if I'm interested in developing soil moisture maps for the whole EAA on organic soils, what do I need?
Soil moisture maps,
Like a dynamic.
it's very dynamic. So what is the advantage of the proposed approach is that we can download in an automated way all the data. We have this opportunity for Florida State. So This day-by-day product, it's time consuming, but if you automatize the procedure, you can do it. So we have this, let's say, the infrastructure in order to do it. Then we have to go with a traditional way, some ground truth data from stations, and we are going to develop the model. We have this experience. I'm not a big fan with soil moisture. I didn't work in the previous years, but as I said, we know how to do it. But I believe that there are a lot of good colleagues in order to collaborate with them and get expertise for the modeling and provide this pipeline in order to automatize the procedure. I don't want to invest time since there are several colleagues working on this. Yeah, but it's easy. It's easy, let's say. Also for them, someone has work on this, right? Yeah, but I know that soil moisture, especially in areas like this, because in Europe we work a lot in Great Britain and also in the north part, the soils are more or less the same like here. A lot of organic carbon, yeah. Actually, I'm from Greece. We don't have organic carbon, so it's more representative like Immokalee.
Um, Thank you, Doctor, for the presentation. It was really good. My question is about the temporal assessment and then the resolution, because I saw the resolution is 30 by 30 meters. Based on what did you guys choose the temporal assessment? Because those parameters that I'm seeing here, they can vary like in the time, in the temporal dimension very quickly. Do you base on the cropping system to choose the temporal assessment? Or, yeah, because what I'm thinking is, what about if somebody has a different management practice that can affect those parameters in here? Because I assume that you use those data that you get from the assessment to train the model, and then you can get. So based on what exactly you choose the temporal assessment.
That's a good question. So going back to this is a product from SWFREC. SWFREC are some colleagues in Netherlands. They work a lot of years with digital soil mapping. They do excellent work, but the limitation is that they work with legacy data. So they develop a model that represents the soil status in 2008. So what we thought that since we have the opportunity to monitor day by day, I think it's here, yeah, day by day the fields, we try to extract the specific information of bare soil pixels in order to have a direct correlation between the bare soil and the dependent variable, the soil property. And based on this, we assess for 1 year all the available data, and we make a mosaic. We make a mean of this in order to get the most representative soil spectral signature within 1 year. I think we try to do this in semi-annual level for pH, but we didn't see big differences within a range of 6 months. For sure, we didn't try to do for organic carbon, because usually in order to see a change after management practice in organic carbon, we request more years. There are examples that after 5 or 7 years, we don't have see anything. So for some properties like organic carbon, maybe it's not important. But for pH, in 6 months, we didn't see any difference, but maybe we have to try something else. So this is under investigation. If we would like to provide information for pH, if it's worth to do it for 9 months, and for organic carbon every 2 years, we can explore this. But you just define the thresholds and you generate the product.
Right. Thank you once again, Dr. Nikos, for your fine presentation. And with that, we hope folks can join us for the following seminar series. Thank you.